to leave that up. How do we make electricity? So there's a couple different ways that we can make electricity. So we talked about a motor, and we can imagine that essentially this copper wire has free electrons on it, and this motor, so if we have this rotating magnet, it creates essentially an electromotive force to move these electrons down this chain. How else can we move electrons? How else can we create an electromotive force? We can make a battery. So a battery is essentially an electrochemical reaction that has a voltage difference, a voltage potential. Remember that voltage is like a type of potential energy? So we have this voltage potential between one terminal of our battery and the other terminal. So here we have electrons essentially flowing this way, but in order to close our circuit inside of our battery, we have an electrochemical reaction going on, and eventually our battery will die. The chemical reaction will slow down and stop when all of these ions essentially balance each other out on these two electrodes. And so in a lead-acid battery, where do we see the lead-acid batteries?
Car batteries?
Old, like essentially a traditional like engine starter car battery, not an electric vehicle car battery. And so this is the chemical reaction going on inside of a lead-acid battery. And so inside the battery we have ions moving around, and then outside the battery we have just the electrons moving around. What's another different way that we can kind of force these electrons to move? Well, what if we could just kind of come along and go all Monty Python on them and just take one of those electrons and kick it? How could we target one of those electrons with enough kinetic energy to get it to move? So we could throw neutrons at it, but that might cause the atoms to split, and that would be not something that you would want on the top of your little scientific calculator. Light. So this is the photovoltaic effect. So what is the photovoltaic effect? Is essentially a light photon comes in, bounces up, comes in with enough kinetic energy to bounce the electrons off of this plate over to here, and then essentially go around. Now because we took the electrons off of this plate is now positively charged. This plate is now negatively charged with electrons on it. Electrons on the negatively charged plate wants to get off of it, and so they then move all the way around to fill in the holes over here. So how do we actually do this? So we, first of all, create silicon crystals. So you may have heard that solar panels or semiconductors in general are typically made with silicon chips. And so if we had a pure silicon crystal, if we had a pure silicon crystal, we had a photon come and hit it. Is this going to animate how I think it will? So essentially, if we had a pure silicon crystal and we came in and bounced off, if this photon came in and bounced off this electron, so then it popped off, that electron has nowhere to go except to pop into the same hole that it popped out of. So how can we introduce holes or extra electrons in the silicon crystal so that when a photon comes in and kicks that electron out, instead of just going into the same place that it was, it jumps to another hole? And so we could either create extra electrons that are just floating around without kind of a bond to hold them in place. So that would be N-type doping with phosphorus, which is wicked confusing because you think that this would be P-type doping, because it's phosphorus, but it's not. So we could have N-type doping with phosphorus, which provides an extra electron, N meaning more negative because you have extra electrons. P-type doping with boron, and if we looked at the periodic table on boron, we'd see that it looks very similar to silicon, but has one less electron. And so that essentially, when it tries to bond with silicon, it can't bond fully here, so we can essentially introduce a hole in the crystal lattice. So let's look at if we were to essentially have a silicon crystal where we p-dope one side of it and n-dope the other side of it, although I think these labels should be flipped because the p-dope should be positive. And so essentially, there's probably a little area where kind of it's all balanced out, but if we have kind of a photon come in here, it's going to want to take one of these electrons, and if that photon has enough energy to not just bump it out into this band gap where it just falls back down to essentially where it started, but if that photon has enough energy to bounce it all the way up to the conduction band, then it could actually conduct a little bit and cause these electrons to essentially balance each other out, which would cause a current to flow through this wire. Because once it kind of turns white like this, there's going to be more electrons that are going to want to dump in over here, which is then going to kind of suck them around from the other side. We'll actually get a current, and we'll actually create both a voltage and a current there. So how do we know how much energy an electron has? Does this electron, how much a photon has? Does this photon have enough energy to bounce one of these electrons from the valence band to the conduction band? Because if it doesn't have enough, if the photon comes in, hits an electron and bounces it, that photon lost all of its energy, but if that energy wasn't enough to move that electron to the conduction band, then there was no conduction of electricity. And so these energies are going to be measured in what are called electron volts. So electron volts are a unit of energy. 1 joule equals 6.2 times 10 to the 18th electron volts. So electron volts are a very, very tiny unit of energy. And so we can say that the energy in this photon is equal to Planck's constant, which is just a pure constant, never changes, times the frequency of the light. And if we don't know the frequency of the light, but we know, let's say, the wavelength of light, we can just divide, we can take the c, the speed of light, and divide it by the wavelength to get the frequency. So often light is given in nanometers. Essentially, that's the wavelength of the light in nanometers, and so like 700 nanometer light is very red, and 400 nanometer light is kind of very blue and purple, and so here we see the opposite of Roy G. Biv, right? It's the rainbow. It's a red, orange, yellow, green, blue, indigo, and violet. And so we can figure out what the energy in this of this photon is by saying it's 300 nanometer light and Planck's constant. And so let's put Planck's constant here, 6.63 times 10 to the minus 34 meters squared kilograms per second. And then speed of light, so I didn't give you the frequency, I gave you the wavelength, so we need to go to speed of light. So this is 3 times 10 to the 8th meters per second, divided by 300 nanometers, 300 times 10 to the minus 9 meters. And so this gives us 6.63 times 10 to the minus 19 joules, which is 4.14